Okay. So yesterday we were discussing about the diffraction grating, and in the end, so I was discussing about a crystal, which so most of the solids they are made up of, or they are like crystals, which are basically your three-dimensional periodic arrangement of atoms. And this uh, periodic crystal or the periodic structure works like a grating. This is equivalent to a grating when we use X-ray as a source, because the wavelength of the X-rays are typically of the order of 1 angstrom, few angstrom, and it is really close to the interplanar distance or interatomic distance that you observe in a crystal. And therefore, these crystals will produce a diffraction pattern when X-rays are incident on this crystal. Now, to elaborate on that, so normally a crystal is, since it is a regular arrangement, periodic arrangement of atoms, so you can actually take a small volume of a crystal, which represents, which acts like a representative of the whole crystal. So that means if you take that small volume, so which we call the unit cell. So this unit cell has all the characteristic of your crystal. So this unit cell is a smallest volume that defines your crystal. So if you repeat now this unit cell in all three directions, then you will create the entire crystal. And unit cells are typically like will consist of few atoms, and so there are let's say if we look at a, so there can so if we consider a structure which has a cubic symmetry, let's say, so if the crystal is cubic in nature, so there can be other types of arrangement as well. So the most simplest one, and more like many of the metals you will find they are in cubic crystal form. So there are three cubic crystal geometry that normally you encounter in 3 dimension. So one is a simple cubic, so where the unit cell would have only atoms at the corner. Okay, so if you take the corners and put your atoms there, so this is your simple cubic unit cell. And now if you repeat this in 3 dimension, so you will obtain a simple cubic, a crystal which is simple cubic, has simple cubic structure. So there is another one which is known as a body center cubic, or BCC. So in this case, you have one atom, so there will be atoms at the corner, and then you will have also atoms, or one atom at the center of this cube. So there will be one atom here at the body center. Then there is a third type of crystal in the cubic, this class, so which is known as your FCC, or face center cubic. So this has atoms again at the corners, and then also at the face center The face center means so it will have 6 faces, the cube. So on each face center, so you have one atom. 1, 2, 3, 4, then top and bottom. So you will also have atoms in the 4 or 6 faces, which makes the crystal HCC crystal. Now, when you look at these atoms, so it is this periodic arrangement. You can actually, so how we say this acts like a grating. Uh, Here we talk about that the atoms, they form a atomic plane, and this one atomic plane makes like or there are like set of these atomic planes which form the your grating uh, for the X-rays. Now these atomic planes, so if I say this is one plane, for example, so this atomic plane, so this is another plane. So similarly, you can have many different planes, and each plane can be identified uniquely using a index known as Miller indices to identify your atomic planes. So this is normally represented by HKL. Okay, so each plane of atom has certain can be identified with HKL index, and that uniquely defines that uh, atomic plane. And when we talk about this crystal, so this cubic crystal, so this has a dimension. So this is a cube, so it has a dimension of A, which is known as the lattice parameter. So this is again very much a material property. So if you take a sodium or iron, so any material, they will have a different lattice parameter. So now these HKL, these values, they for different this cubic crystal, the HKL values can be different because they will uniquely identify the atomic planes. Now, how do we realize that there is it acts like a grating and there is a diffraction due to that? So let's look at this picture here. So this is representing a set of planes which we will identify with HKL indices. So you can actually, I think you already know about Miller indices. Am I right or not? So in chemistry, you must have already studied about Miller
No,
indices.
sir. No, sir.
No or yes?
No, sir.
No, sir.
No, sir.
Some are saying
Yes,
yes,
sir.
some are saying no. Okay. So Miller indices are basically nothing but like a intercept. So if you take a plane and you take an intercept on your XYZ axis on a Cartesian coordinate, so you can then find out from the intercept what is the Miller indices of that plane. So for example, so there is a general way of calculating it, but let me first give an example and then we will look at the general formula to calculate that. So let's say if you have, so if I take, so again we look at the cubic crystal. Okay, so and I define my axis, the coordinates, like let's say this is X, Y, and this is my Z. Now each plane, so you can, any atomic plane that you talk about will have some intercept with this XYZ axis. So for example, if I take now this plane, for example, So it is parallel to your xz plane. So that means the intercept for x and z will be, so if I calculate the intercepts, so the intercept for this plane will be along x-axis, it is at infinite, and y-axis, let's say it is cutting y-axis if the parameter is a, so it is at a, and the intercept for the z-axis is infinite. And then you take the reciprocal of it. So reciprocal means, so you take 1 by infinite, 1 by a, 1 by infinite. So this will be 0, 1 by a, 0. And then you multiply here by a, so that you get an integer value, multiply by a. So you will have 0, 1, 0. So this plane is identified with a HKL value, so 0, 1, 0. So similarly, if I take so the general formula for calculating this Miller indices for a plane is you have to find the intercept, and then you take the reciprocal of that, and the third thing is you multiply by the LCM of the denominator, so that you make it an integer. So multiply by LCM to make it an integer. Okay, so you cannot have fraction here. Okay, so you cannot have half in the HKL value, can never be fractional. Okay, so they are always integer. And normally you represent by closing this like a bracket like this, so that represents your HKL plane. So if I take a 1 plane, so how would it look like? So if I say my HKL value is 111, so in that case the intercept should be, so you can go in the reverse order. So the intercept would be this plane would intercept your XYZ at, let's say, A. This is for a cubic crystal. So this what we are giving example is only for cubic crystal, but this rule, it is true for all kind of crystal structure. And you have this so all possible combination of these HKL values, integer HKL values are possible. So you can have 0, 1, 0, you can have 0, 0, 1, or you can have 1, 1, 0. Okay, so these are all possible HKL values which correspond to different crystal planes. Okay? And these are all represent a set of parallel planes. So now this axis has HKL value 1010 that we calculated. So this one also has the same 010. And then if I take another cube next to it, so let me draw another cube here, which is the next unit cell in the crystal. So this plane is also a 010 plane. So all these parallel set of planes are represented by this HKL value. Okay. So similarly, if I take in any direction, so I will have a set of planes which will be represented by this HKL value. And you can have many possible combinations. So 110 or 110, 011. All these possible set of planes will represent, or Miller indices are representing a set of planes. So 111, you can also have 211, 311, 200. Okay, so all these actually are representing a set of planes in a crystal. Okay. So uh, so how this is related to this value A. So we said we have this set of plane which represent by HKL values, and now so most of the planes will have certain interplanar distance, or let's say, let me go to this picture here. So now let's say if I take a some arrangement here. So these points that you are seeing, they are atoms, okay, position of atoms. And so this represents one plane, this is one plane, this is another plane, and so on, okay. And these each all these parallel set of planes will be represented by a HKL value. So now in the same arrangement, if you observe closely, so we can also have a set of planes in this direction, okay. So if I now look at this, so I will have a set of planes in this direction also. So this will have a different, so let's say it's 2K2 L2, this will have a different value. So I can also have another possibility here, another set of planes. Let me take a plane like this, okay. Okay, so this is another set of planes here in the same crystal, okay. So this is this can be represented by another value of HKL. So all are always integers. And so the same crystal and same set of arrangement can have different HKL values depending on how you are looking at it. So if you are looking from this direction, so you see this HKL value. So if you are looking from this direction, the HKL value is different. Now if you are looking from this direction, then HKL value is different, okay. Now how it is related to the lattice parameter A? We said your cubic crystal is defined by a lattice parameter A. So how it is related? So normally the relation is so each set of planes have a separation D, okay. So we say this is D HKL will be related to, in a cubic crystal, will be A by H square plus K square plus L square. So this is how your lattice parameter A and your interplanar distance D are related. So if you know what is the lattice parameter and what is the HKL value, so you can find out the D, or vice versa. So if you know what is D and you know what is the HKL value, so you can calculate the lattice parameter of the crystal. So these setup planes will represent, now they are acting like a grating, okay. And your grating element, like what we said, is basically your interplanar distance, this DHKL. So under what condition you will observe a intensity maximum? So to observe a intensity maximum, you would expect that there must be a constructive interference after the diffraction. So after this is the X-rays are diffracted, so you should have a constructive interference that would lead to a maximum intensity. So, and what is that condition? So if you look closely, so let me draw here just one set of plane here. So let's say this is what I am looking at as a plane in the crystal, and X-rays are incident at angle, let's say this is theta, okay. So this is the glancing angle. So now we are saying the angle is with respect to the plane. So normally you define your angle, this is your incident angle, you say, but in a X-ray diffraction measurement, normally we talk about angle with respect to this atomic plane. So this is the glancing angle, okay. So there is a little bit different in the nomenclature. So this is the glancing angle. Now what is the path difference? The path difference between these two, so these two waves will interfere constructively if you want to observe a intensity maximum. And that means the path difference, if path difference is an integer multiple of lambda, so you will observe an interference pattern. So in order to calculate that, so we will draw a perpendicular from this point to this one. So this is your 90 degree D, this is your D, So this is theta, means this value is also theta. Okay, so this is also, this angle is also theta. So this one will be d sine theta, and this one will be also d sine theta. So the extra path that is traveled by this ray here, the second one, is 2d sine theta. So this is the path difference between these two waves. So the path difference is 2d sine theta, and if this is equal to your integral multiple of lambda, so you will observe a constructive interference, and you will have an intensity P, which this law is known as your Bragg's law. So this tells you that if you know what is the X-ray wavelength, and if you can find what is the angle where you observe the intensity maximum theta, so you can calculate what is the interplanar distance d. And if you can calculate this d, and you know what is HKL value, so you will then find out the lattice parameter. So normally you would write in a more general form, it is d HKL sine theta should be equal to m lambda, and m is basically your 1, 2, 3, so some integer, and so this is the order of diffraction that we are looking at. Now, how it manifests in this cubic system. So let's say if you take a cubic, a simple cubic, for example. So now in a diffraction grating, also what you have is you don't, sometimes you will also have that some missing order diffraction peak or missing order also exists. So that means all the planes may not lead to a constructive interference, even if they satisfy this Bragg's condition. Okay, so even if they satisfy the Bragg condition, so for some arrangement of atoms or for some values of HKL values, you will have a situation where your the intensity will be 0. Okay, so what are that condition? So this condition is different for this simple cubic, BCC, and FCC. So if I take a simple cubic, so for a simple cubic crystal, so all lattice planes should, so or crystal planes or lattice planes will diffract. So that means the Bragg's law will be satisfied for all Miller indices. So example, if I say 100, 110, okay, so 200, 210, and so on. So all possible values of your the all possible HKL values will lead to give rise to a constructive interference when the Bragg's law is satisfied. But if you take a BCC lattice, so those planes which have only, if H plus K plus L is even, so then those planes will only produce a diffraction. So that means other planes, other values for other values of HKL plane, so they will exist, but there will be no constructive interference. You will never observe for that. So we'll not go into the calculation of that, but I just want to point it out, and you will see why I'm doing that. So let's say if I say H plus K plus L should be even, so what is the possibility? So 110 I have to rule out, because if I add the HKL values for 100, that is odd. So 110 is a possible plane which will diffract. So 200, of course, then I will have 211, and so on. So what is missing here? 100 is missing. Then this 210 is missing. So some of the the planes that exist in the crystal, so they will not give rise to any diffraction pattern. So if I take FCC, the condition for diffraction is also different. So in that case, the condition is HKL are all odd or all even. Okay, so what it means, so example will be your 111. So this is all HKL values are odd, so they will diffract. So all even, so 200 will also be present. Now 110 will not exist, 211 will not be there because they are not all odd. So there is a mixture of odd and even HKL values. So then you will have 220 is a possible, will give rise to a diffraction pattern. So 311 will give rise to a diffraction, will satisfy the Bragg's condition. Okay, so you can see there are missing orders depending on what is the type of the crystal. Okay, so how we can calculate this angle of diffraction? So from the, so we know that the Bragg's condition is HKL sine theta equal to lambda. So let's say we consider only the first order diffraction peak, because the higher order peaks are very weak and normally will not really observe in X-ray diffraction measurements. So here the DHKL for a cubic crystal, we said is like this. That means your sine theta would be equal to lambda by 2a square root of h square plus k square plus l square, which is, you can write it down right by n. And what is n? N is your sorry, square root of n. So where n is your h square plus k square plus l square. So now if we want to rephrase the condition of diffraction for simple cubic and FCC and BCC, so we can rewrite in a rephrase it in a different way. So for simple cubic, so diffraction peaks will be observed when so when n, the value of n is equal to 1, 2, 3, 4. Okay, so all, because all combinations are there, so all planes are basically will contribute to a diffraction pattern. So the value will be 1, 2, 3, 4. All integer values would exist. So this first one would correspond to a 100 or 010 or 001. So these planes would make sure that n equal to 1. So that condition is satisfied. Then this 2 would be 1, 1, 0. Okay. This is the plane, HKL plane, which will satisfy this n equal to 2 and also contribute to the diffraction peak. So 3 would be 111. Okay, so that is 3, 111, and 4 would be 200. Okay, so and so on. Okay, so all these lattice planes will produce a diffraction. Now, what is the condition for BCC? So BCC, we said H plus K plus L should be even. So in that case, N would be, so when you take the square, so this is always would be even. So that means N should be value 2, 4, 6, and so on. So all even number, when N is even, so then you will observe a diffraction peak, and then you say this is a BCC crystal. Now for FCC, the condition is HKL odd or even. So all odd or all even. So what it means for N, So n will be, so when you calculate n, so in that case, so you will have these values. N will be equal to 3, 4, 8, 11, 12, 16, and so on. So this 3 would correspond to the 111, then 4 would correspond to 200 HKL plane, 8 would correspond to 220, 11 would correspond to 311. So there are a lot of missing orders here in case of FCC. Okay. So using this relation, so you can calculate, so this, for different crystal types, so you can calculate what should be the angle which will give rise to your maxima, intensity maxima. So for example, if you take a X-ray, so if your X-ray wavelength is 1.54 angstrom, which is your copper K alpha 1 line, and you use a your crystal is sodium crystal, which is BCC, then the corresponding values of theta, you can substitute that. So you will get values like 14.7, 0.3, 21.03. So at these values of theta, you will observe the diffraction peaks. So one interesting thing which you can see immediately, that if you take a ratio of sine theta 2 by sine theta 1, so in each case, let's say look at this ratio, sine theta 2 by sine theta 1. So what would be that ratio? So sine theta is nothing but lambda by 2a square root of n. So this lambda by 2a would be always the same. So what is changing? Only this n value is changing. So if I take sine theta 2 by sine theta 1 for simple cubic, so n is any possible 2, 1, 2, 3, 4. So for simple cubic, this value would be 2. For BCC, this is again all even. So we take the first one is 2, second one is 4. So 4 by 2, this is again 2. Now for FCC, this value is different. So it is n is 3. First is 3, the second is 4. Okay. So this ratio would be 4 by 3. So now if you calculate, so this is a way of distinguishing from the diffraction measurement. You can clearly say whether your crystal is FCC or BCC. Okay, so if you perform a diffraction experiment, X-ray diffraction experiment, so you find out what is the theta value where you observe the peaks. Now you take the ratio of at least the first one, and if that comes out to be 4 by 3, you immediately say it is FCC. If it is not 4 by 3, so either you will say it is BCC or simple cubic. But again, you cannot really distinguish from this method the difference between BCC and simple cubic. Okay. So typically this X-ray diffraction measurements are performed. This is an example how it is performed. So there are different methods. So basically what you have is you have a incident wave with this is known as a powder diffraction. So I'll give just 1 minute here so you know how this experiment is done. So you have a incident wave with a X-ray with lambda, which is the wavelength lambda. Then you have a polycrystalline powder sample. So what it means? So this powder sample means you have your lattice planes are randomly oriented. So you have many such tiny crystals, so many powders or particles which have certain orientation, crystallographic orientation, and all these orientations are random. So that means the HKL values are all random within a sample. And when you do this kind of experiment now, so now you have one wavelength, but you have many HKL planes which will lead to a diffraction pattern, and you get a ring. You form this ring, which known as a Debye Scherer ring. So you will produce this ring like pattern. So where you have a distribution of HKL planes within the sample, and each HKL plane will lead to give rise to a different ring. So each ring here represents a one HKL plane. Okay, so this is another H prime, K prime, L prime, and so on. Okay, so this is how you perform the experiment, and normally you will observe this intensity peak as a function of theta from the experiment. So once you know what is the value of theta and you know what is lambda, so you can calculate and you know what is which plane it is, HKL plane. So then you can then calculate D and A. Okay. So any question so far? Okay, so if not, so let me go to the another topic which I wanted to introduce to you, because there is not enough time, but it is an important concept that you should know. So this is a polarization. So what is polarization of a wave? So when we say any transverse wave, so there is always, it is associated with a displacement. Okay, and the displacement will be along certain axis. Okay, so if it is uh, fixed to a particular axis, this displacement, then we say the wave is polarized. So for example, so if I say I have an electric field, uh, which is I'm writing like this. Let's say Ex is 0, Ey is equal to, or let's say, sorry, Ex, I'm writing it. So I'll write, it is the oscillation of electric field is along X axis. So I will write the wave like this. Ey is 0, Ez will be equal to 0, and in that case Hx will be 0, Hy will be H0 cosine kz minus omega t, and Hz will be equal to 0. So this is an electromagnetic wave where the displacement of electric field is along X, and therefore the displacement of magnetic field is along Y, and it is propagating along Z axis. So this kind of wave, we will call it is a linearly polarized wave, or sometimes also known as a plane polarized wave. So that means the polarization, the electric field is always oscillating along the x-axis, one of the axis. So this is known as a polarization. But most of the light sources are unpolarized. So that means your incident electric field, because it's a vector, so it can actually oscillate in all possible directions. So there is a random orientation of electric field when this light waves are produced, and therefore like your sunlight or your light, your sodium vapor lamp or any light in your room that you have, it is unpolarized. So there is a way to produce polarized light, but before that I just want to give an idea like different kind of polarization you can observe actually. So one is, this is the linear polarized one. Then you also have a circular polarized light, where you see that you have two waves now. So one wave, the electric field, there is a phase difference between the two electric fields, which are oscillating perpendicular to each other now. So one is this one, okay, this is one wave, and then there is a phase difference about pi, or path difference of lambda by 2, and you see another wave which is oscillating perpendicular to that. So when you see this kind of combination, so you get a circularly polarized light. So where you say, so both waves are the amplitude same, the phase, there is a phase difference. There is phase difference of pi. Now you can also have an elliptically polarized wave where if you have a different amplitude now, so the electric field would look like, so when you're looking from this direction, this is your, let's say, I. So when you are looking from this direction, so it would look like the electric field is rotating in a circle, okay, because the amplitude is same. Now if the amplitude is different, you will observe a elliptical polarized wave, okay. So again, you need two electric field which are propagating together with certain phase difference. So this is how normally different kind of polarized waves are seen. But now we will look at how linear you can produce this linear polarized waves. What is the different ways one can do that? So the simplest way is like if you pass through a Polaroid. So there is a material known as a Polaroid. Okay. So you can use that. And so if you have an unpolarized light, let's say, so this is, I have an unpolarized light. So that means my electric field is oscillating in all random direction right now. So there is no particular direction along which the wave is propagating or the electric field is oscillating. Now I put a Polaroid here, and the Polaroid will have certain axis. Let's say this is the axis of polarization. Okay, this is, let's say, x-axis, I would say. So that means the wave that comes out will all be polarized in this direction. So this is, you will get a linear polarized light using this Polaroid, which has a polarization along x-axis. So now if I put another Polaroid here, so let's say I have a polarized, unpolarized one. Now I put a Polaroid which axis this direction. So I get this plane polarized or linearly polarized light along x direction. And I put another Polaroid here, which I can rotate. Okay. So again, it has certain direction, the polarization direction, which I can rotate. So now if the intensity that I will get here, if I use another Polaroid, so will be given by I naught cos square theta. And theta is the, theta is basically the angle of, so this is your first Polaroid, this is the second Polaroid, angle of P2 with respect to P1. So you will have maximum intensity when I equal to I0, when theta is equal to 0. So that means they are parallel. Now, if you change the orientation of P2, so you will observe a decrease in intensity. And then when theta is equal to pi by 2, so your intensity will be 0. And so on. So this is one way of producing your linearly polarized light. Another way is also very interesting phenomena that you observe by reflection. Okay, so this is a concept where we are saying the light is just transmitted through a Polaroid, a material which is has a property that it will only allow one set of electric field, one axis to pass through it, depending on what is the polarization axis. And then you can also obtain by reflection. Yes.
Excuse me, sir. Sir,
Yes.
is there no magnetic field in light?
Magnetic field, yes. The magnetic oscillation is also there. Yes. So magnetic, whatever if the electric field is oscillating in, so the the oscillation of magnetic field will always be perpendicular to that. So normally when we talk about polarization, so we just talk about the electric field, and automatically if you know what is the electric field at the position x and at time t, so you can calculate what is the magnetic field there, right? So it is just a relation that you know from the Maxwell's equation, you can calculate. So therefore, normally when we define this polarization, we only talk about electric field, and inherently it is assumed that magnetic field is perpendicular to that electric field. So now when you say it is unpolarized, so electric field is random, when you look at a point x and any time t, so electric field will have a random direction, okay? So it can be sometimes it is along x-axis, sometimes y-axis, sometimes in between x and y, okay? So if it is propagating along z, let's say. And similarly, at that instant, so if you look at the magnetic field, it will be exactly perpendicular to that electric field, okay?
Yes, sir.
Okay. Uh, so you can also produce polarization by reflection, where so if I take a, let's say I take a polarized light, where the polarization of our electric field is in the plane of the incidence. So this is my plane of incidence is this normal to this surface. Okay, so this is refractive index n1, this is n2, and this is, let's say, the angle of incidence theta. Now, if I have such a wave, which is, we will call it as a p-polarized wave, what we are assuming here is that the electric field is in the plane of the incidence, okay? And for certain angle theta, so when theta would be equal to tan inverse n2 by n1, so which is known as your theta p or Brewster's angle. So what would happen in that case? That you would have a situation where there is no reflection. So no reflection will take place. So only you have a transmission of the wave, and the polarization will be again, it is remains the, so there is no change in the polarization here. So you will get no reflection, okay? So this is known as the angle theta p, Brewster's angle. So if I take a air water interface, so this theta p is of the order of 53 degrees. So now if my incident light, if I incident at 53 degrees, so I will have actually no reflection. Or theta is theta p or greater than that. Now, if what happens if I come with a unpolarized light, so if the incident light is unpolarized, so this is the situation if I have this p polarized light. So what is the situation if I have an unpolarized light? So again, this is theta p, let's say, and this is a unpolarized. So what would happen in that case? So in the transmission one, you will always have this p polarized light. Okay, so this is p polarized, and the reflection is normally known as a s polarized light. So what is s polarized? Where the electric field is now perpendicular. So dot means it is perpendicular to this our paper plane of the paper, or this plane of incidence. Okay, so this is perpendicular to that. So now electric field is basically perpendicular. This is oscillating perpendicular to that. So you can get a polarized wave if you satisfy this condition under a reflection. Okay, so this had some application or nice these concepts are used for when we use the eyeglasses, this polarized sunglasses, for example. And another interesting thing is this double refraction. So we will talk about that a little bit more. What is double refraction? So if you take a crystal, okay, so we have taken a crystal. This is a calcite crystal, okay. So this is known as calcite, a very specific crystal. So if you pass your light through the calcite crystal, so what you observe is there are two waves or two rays that you actually obtain in the transmission. So your input is one ray, but what you obtain, you see two rays, okay, in the calcite crystal, and that is due to a double refraction, okay. So we will see what is this double refraction is. And interestingly, what both the waves are actually also linearly polarized. So both the waves will be, so you come with an unpolarized light and you pass it through a calcite crystal and you obtain two rays and both are plane polarized. Okay, so that is the nature of the crystal. So here on the right hand side, you see this example of double refraction. So when you look at so here they have written calcite crystal and you put the crystal and you see actually two, so it looks like you see two things written, two times this calcite is written because of this double refraction. So what is this double refraction? So in a very simple way, so if I say I have a incident wave on a calcite crystal, okay, and now, so this is a unpolarized one. So what I would get is one wave which just propagates like a normal wave. This is known as a ordinary wave or O wave or O ray, okay. And then there is another one which travels in a different optical path. So this is known as an extraordinary wave or known as E wave or E ray. And interestingly, this O wave has a polarization which is the electric field. So this is an unpolarized one. So you will have the polarization perpendicular to the plane here, and here the polarization is in the plane of the incidence. So this is what you will obtain, and this is known as a double refraction. Okay, so one is just passing through like a normal or an ordinary wave, so no refraction, nothing is happening, and the other one takes a different optical path and the polarized. So this is the nature of the crystal. Okay, so you will not have it for any like a glass or anything. Okay, so you observe this only in this calcite crystal. So this is how you can also produce a polarized wave. Now there is this O wave and E wave. They have certain characteristic. Okay, so what are those? So O waves actually will follow your Snell's law, and E wave they don't follow. Okay, Snell's law. And what is the velocity? Is it same or different? So they are actually also different. So if you look at the velocity of your ordinary wave, the velocity is given by c by n0, where n0 is the your refractive index for the ordinary wave. Okay. Now the corresponding velocity VRE. So this is, let's say, velocity of E wave, and it is different, and most importantly it is different in different directions. Okay, so this velocity of E wave, it is different along different direction in the crystal. So ordinary wave, it has the same velocity in all directions, but your extraordinary ray has a velocity which is different from ordinary wave, and it is also different along all different directions. So how it is depends on the direction. So this is given by this relation sine square theta by c by ne whole square plus cosine square theta divided by c by ne whole square. Okay, so this is how the velocity of your extraordinary wave is related to the material. And Ne and N0 are basically your refractive index, corresponding refractive index, and it is like different. So the Ne is different and N0 is also different. So they are not the same. Now, if you say theta is equal to 0, so what is the case there? Theta is 0. So this term will be 0. The first term is 0. And second term, so your VRE will be equal to C by N naught, which is equal to VRG. So that means along a certain direction, okay, so along certain axis, it is possible that both extraordinary wave and your ordinary wave have the same velocity. And that direction is known as the optic axis of crystal. So if I have the crystal and this is my optic axis, so this is a Z, which I define as optic axis, and now my wave is incident along this direction, so both E and O wave, they will travel at the same velocity. But now if the light is incident along this direction, so E wave will travel at the same velocity like always, but O wave will travel at the same velocity, but the E wave will travel at a different velocity, which is defined by this equation here. And if you look at this equation, it is an equation of an ellipse. Okay, carefully if you look at it. So it is an equation of an ellipse. So that means if I draw actually the velocity profile, so let's say I take a situation where this is my optic axis. So my ordinary wave would be traveling like isotropically in all directions. So this is an isotropic. So crystal is isotropic, known as isotropic for ordinary wave, and it is anisotropic for E wave. Okay, so the crystal is anisotropic for E wave because your velocity depends on the direction. Okay. So this is the velocity profile that would look like. This is, let's say, Z axis. Now, what would be the velocity profile for the E wave? So that depends on what is the relation between Ne and No. So let's say if I say theta is equal to pi by 2, in that case, what would be the value of VRE? So you go back to this equation. So theta is pi by 2. So the second term will vanish. So you will only have the first term, and VRE would be equal to C by Ne. Okay. So now you have two possibilities. You don't know what is the value of Ne, the refractive index of extraordinary. So if Ne so if Ne is so one possibility is Ne is less than N0. Okay. So in that case, what you have is the velocity profile would look like so your VRE. So when you are talking about theta is pi by 2, so VRE, Ne is less than N0. So VRE will be greater than VRO, right? Because Ne is less than N0. And in that case, this is known as a negative crystal. Okay, so this is known as a negative crystal, and along the optic axis, both will have the same ordinary and extraordinary will be the same, but along the pi by 2, so you will have a ellipse, formation of an ellipse, the velocity profile of E wave. So this is your E wave, and this is your ordinary wave. So this is for a negative crystal. This is how it would look like. Now, if you take a positive crystal, so situation would be different now. So if this is my ordinary wave, the extraordinary wave would be like this. So when this is for a positive crystal, when Ne is greater than 0, and in that case VRE will be less than VRO when theta is pi by 2. So this is the velocity profile that will obtain. So there are some other characteristics which are interesting. So one particular, so few of the characteristics are just I will point out. So both E and O waves are linearly polarized. Okay. Then another, so if I talk about the electric displacement, so it will be always perpendicular. So this will again follow the same Maxwell's that condition, that the k vector, propagation vector, will always be perpendicular to both your displacement electric field and displacement electric displacement for the both the waves. Okay, so both will be following the same Maxwell's equation. There is no change in that. Only additional thing would be your since the polarization is changed. So if I take the displacement, electric displacement with the propagation direction, oh sorry, your optic axis, this is always will be 0. So that means your displacement, electric displacement, is always perpendicular to your optic axis for this is O wave. Okay, so this is for both. D dot K will be 0 for both O wave and U wave. And another, but this D dot Z cap will not equal to 0 for U wave. And that's why the polarization will be different. And you see this leads to this double refraction, which normally is used to produce linear polarized light. And I think I will stop here because it's already time. And yeah, any question? So you can read a little bit more about this double refraction from the book that nicely explains how this E ray or E wave and O waves are produced and how they propagate, example, when there is a normal incidence. Okay. Yeah, another thing which I want to share, that there was some question regarding this Michelson interferometer. So I will post some videos and some additional reading material, then things will be clear. So to answer that question, whether 2D cosine theta should be equal to m lambda should be maxima or minima, it can be both. So depends on what setup one is using. Okay. So I will post a couple of videos and also some reading material. You go through that, then it will be clear. Yeah, any other question?
So the syllabus is complete now for the
Syllabus, I mean, we have not completed, let's say, some application like for what was intended, this.
so
For
those
example,
questions will not be in the test.
no. So whatever we covered in the class, that will be. So for the syllabus, what we have decided, so 15 marks for the what Professor Ambes Dixit covered from his part, it will be 15 marks. So 15 marks from whatever Professor Monica Sinha, she covered, and 10 marks from my part, from optics part. So total is 40 marks. Okay, and all questions are short answer type, some numerical or some like you have to write some explanation.
Okay.
Sir,
So there is no objective type.
sir,
Yes.
Sir, can you please just repeat the marking thing?
Yeah, marking. So what Ambeshi taught. So from that part, it is 15 marks. What Professor Monica Sinha taught, from that part, it is 15 marks. And from optics part, it is 10 marks. So 15 plus
And the
15.
paper pattern?
Hmm? Pattern will
Paper.
be all short answer type or some numericals. Okay. So you have to write it in paper, scan it, and upload it in Google Classroom.
So how
So the
many
There is
final
no
paper
objective
should
type.
be 40 marks. And
Hmm?
some should be 40 marks.
NSEM is 40 marks. Yes, total.
questions are there?
That I depends. So maybe like total would be around 12, 15 questions. So each question you can assume on average will carry it between 2 to 4 marks. Okay, on average it will be 3 marks questions.
Sir, there is no objective part in paper.
What? No?
Objective part.
No objective. No, no, no. There will be no objective or MCQ type of questions. No. Okay. Any question? So we'll have the quiz then Sunday. And regarding the question, there was one mistake in the options that I gave on this impedance one. So I will give 1 mark to everyone in that case.
Excuse me,
Sir,
sir.
Yes.
Sir, can we
thank you, sir.
open the book during the exam?
No, no, it is closed book. So no, it is not open book. So you are
Okay.
not allowed to use your look at book. So you can use calculator, that I can say. You can use so just use your plain paper for any rough calculation as well. So I think you have to share your screen as well when you are giving the exam, and so you cannot use any online material or anything. So you also cannot use any book or any material that has been shared.
Sir, can we use mobile phone
No,
or
no, no,
calculator
nothing.
or calculator?
Calculation you use no, don't use mobile phone. I mean, it's
Sir, can you scientific calculator? Sir, we can use
calculator.
the
You can use,
calculator on our
yes, normal
computer.
calculator you
It
can
will be
use,
on
yes.
screen share.
But even if let's say because you will be doing the calculation, so even if you do not complete or give the final answer, that is also fine. At least from my side, it is fine. So if you answer if I know you have done the steps properly.
Sir, can we use our offline notes that we have made?
No, 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 no. It is just like a normal exam, like you are giving in here. So you cannot
Sir,
bring anything. So the point is, if the invigilator finds it out, so you will be disqualified immediately because we will not be there as invigilator.
sir,
So some
RLC ma'am have given the permission for opening the book.
who
No, sir. Simply there's nothing like that.
who gave?
Sir, I want to ask you about the yesterday quiz. So when
Uh,
I submitted yesterday, it was showing 4 marks, but when you gave the answer, so I recheck it again in the night. So when I viewed the score, it was showing 0/0. So what is that?
but now I think you can see the score again. I think there was a mistake somehow in the Google form. The answers or the whatever mark somehow it was lost. I don't know how. So I saw after your mail it was showing zero, but then I
Yes, sir.
again put the marks to all the questions, and then again you should be able to see the marks again.
Okay, sir. I am checking now.
Mhm.
Excuse me, sir.
Yes.
Sir, a little doubt regarding yesterday's quiz.
Mhm.
There's a question that said, which of the following will show Young's double slit, which will show which will show the pattern, interference pattern. So the
Mhm.
Yes, sir.
options were heat, electrons, X-ray, and water. So
Mhm.
heat is just infrared